Greetings, Doctor. I'm Dashani Rajendran, S55538. The reaction that's involved with organometallic catalyst that I've chosen for this presentation is hydroformylation. Hydroformylation reaction mechanism is also known as hydrocarbonylation, where the hydroformylation of alkene is one of the most important homogeneously catalyzed processes in industry to produce bulk chemicals. In this reaction, what happens is that alkene, carbonyl and hydrogen gas reacts to form an aldehyde that contains one extra C than the original alkene, where the extra C comes from carbonyl. In this reaction, cobalt and rhodium complexes are used as catalyst. Moving into the cyclic mechanism of dissociative hydroformylation reaction mechanism for the formation of the linear n-aldehyde, this reaction is catalyzed by using homogeneous rhodium-based catalyst as shown in the diagram. Pre-catalyst complex rhodium dicarbonyl L2 hydride, where the L is either phosphine ligand or more carbonyl, uses one carbonyl to yield electron deficient 16 electron rhodium carbonyl diphosphine hydride. The L could be either phosphine or carbonyl. Whether the phosphine ligand is monosubstituted or disubstituted depends strongly on the nature of the phosphine ligand and is still matter of discussion and an ongoing research. However, kinetic modeling using phosphine ligand under industrial conditions suggests that the dominating catalytic active species are monosubstituted by the phosphine ligand. Moving on, alkene coordination occurs via transition state 1, which is thermodynamically favored through decreasing basicity of the phosphine ligands. This step is followed by hydrometallation towards the branched or the linear alkyl complex. The formation of the alkyl complex is considered as the regioselectivity determining step, as the N to iso ratio is influenced by the steric and electronic properties of the catalyst and the substrate. As the C atom of the substrate, which is carbon atom of the substrate, coordinated to rhodium, has a partially negative charge, as can be seen here. Electronic character of organic groups connected to it will either stabilize the branch or the linear isomer. The R-accepting groups with pi-accepting character, which is aryl and alkoxy groups, can stabilize the charge distribution better for the branched alkyl intermediates, while the sigma-donating groups, which are alkyl groups, lead to the stabilization of the linear alkyl species. Carbonyl coordination comes next to alkylation that brings to the formation of this alkyl complex. The complex is then acylated through next transition state that results in the formation of complex 6. This complex 6 can also be converted into the resting state complex 7 depending on its carbonyl pressure, which is considered as a dead end to the catalytic reaction. But complex 6 can also undergo oxidative addition of hydrogen to form this n-aldehyde. The reductive elimination via next transition step brings back to the product formation and the regeneration of the catalytically active complex 2. That is basically all about dissociative hydroformylation reaction mechanism for the formation of the linear n-aldehyde catalyzed by rhodium complex. That's all from me. Thank you for your time.